estamos. Perfecto. Buenas tardes a todos. Bienvenidos a esta sesión del Seminario Chileno de Probabilidades. Hoy tenemos el placer de tener con nosotros a Hagop Tossounian. Creo que lo pronuncié muy mal, Hagop, así que discúlpame. Que nos va a hablar está bien, respecto a la Entropic Chaoticity and Fisher-information type chaoticity for a family of rescaled states, que es un trabajo en conjunto con Roberto Cortez, que también va a estar en la audiencia.
Okay. Well, thanks everyone for this opportunity to present my work in preparation with Roberto Cortez. So if you don't know, I will introduce all the definitions necessary, so you don't need to know what the chaoticity is in the context of kinetic theory. And the outline of the talk will be the definition of chaoticity according to Mark Kac, and a motivation with a couple of examples of the chaoticity and how it was used. Then we'll introduce stronger forms of chaoticity, which are entropic and Fisher-information chaoticity. Finally, we will introduce conditioned tensor products which exist in the literature, which are chaotic to a specific probability density function. Finally, the main results will be at the end, where we'll introduce a new family of probability measures and show that this family of measures is going to be chaotic in three ways, in the sense of L1, in the sense of entropy, and in the sense of Fisher-information. And all questions are welcome. So the worst thing is that I might not know the answer. Okay, so let's start with the definition. We start with a family of measures, Fn. They are symmetric probability distributions on n variables, which means these are functions of x1 to xn, and if we interchange any of the two xi's, then the fn's do not sense them. And so these fn live on different spaces, larger and larger spaces, and we call them chaotic if for any bounded and continuous test function phi, which depends on a fixed number of k variables, the limit as n goes to infinity of the integral of fn against phi converges to a product structure, h of x1, h of x2, h of xk integrated against phi. And this is true if phi depends on any fixed number of variables k. In this case, we say that the family Fn is chaotic to h. An obvious example of a chaotic sequence is if we take a product, so resulting from independent random variables. So if we integrate a product against k variables, so the n minus k h's integrate to 1, they disappear, and we're left with a product. So the good news is that this chaoticity allows for some flexibility. We don't have to be this product, as we will see in a couple of examples. Okay, a classical example is, at least due to Meller, 1866, it's known as Poncares Lemma. I don't know if this is the earliest source. So consider the uniform distributions on the spheres Sn-1, it's where the sum of the squares of, well, the norm of the vector v squared is N.E. In this talk, E will denote a fixed constant. We think of it as the average kinetic energy of a single particle. So on these larger and larger spheres, it's a nice exercise that if we integrate any continuous function on k variables, then against the uniform probability distribution sigma n, that their marginals go to a product of the Gaussians, centered Gaussians with the same average kinetic energy E. So here, as we are letting the number of particles or variables go to infinity, we are keeping the average energy per particle, or the magnitude of V squared E, fixed. Okay, and another example, which was motivated from virology, I saw this on a YouTube video, is if we consider a set of n jars, n boxes, and we have 8 times n, let's say, ping pong balls, and we can put them in any way we like into the boxes. If we let Fn be the uniform probability on each of the possible configurations, then it's also a nice exercise that if Bi is the number of balls in box I, then we can take any finite marginals and see that in the limit as n goes to infinity, that the probability of the number of boxes, the number of balls in a given box being equal to m, in this case has the Poisson 8 distribution. So in this example, the Fn is chaotic to Poisson 8 low. So 8 is the average number of balls per box in this case. Okay, here's the result. I think it's by Hiroshi Tanaka. I use Stateman's book to find it out. So if we have a family of this probability densities, I'm going to restrict to densities here, on the spheres of radius N.E. If they are symmetric under the exchange of particles, then the following are equivalent. So if Fn is chaotic to some limiting mu, which means if its marginals converge to mu, products of mu, or if these are in different spaces, we can put them in the same space by considering the random variable, which is measure valued. It's the sum overall components xj. Here I've forgotten to mention that xn is a random variable having low fn. This random measure converges in low to mu. It's equivalent to fn being chaotic. Well, in application, one can see in an application that we can take the expectation of a Wasserstein distance between this is called the empirical measure, which is random valued, and the measure mu. If this goes to 0, then the family Fn is chaotic to mu. Of course, by the Wasserstein 2 metric can be defined in terms of couplings. So here, the definition is the square of the Wasserstein distance is the infimum of the quadratic distance between x and y over all measures whose first marginal is mu1 and the second marginal is mu2. Okay, so far, this is what chaoticity means. So it's like a weak kind of independence of the marginals. Let's see an example of why this was introduced. So Mark Kac introduced a toy model in 1956. I will not describe all the describe the model, just the things we need from the model. He had a bunch of n particles in a space homogeneous model. So the space only deals with the velocities, where he allowed for binary collisions, which means 2 particles can collide at a time in such a way that their velocities get updated, but the sum of the VI squares is preserved. Hence, and for his model, he showed the following, that if Fn of t, which depends on n variables, he considered distributions in L2. So if the Fnt are supported on the sphere, and along the time coordinate, they solve what he called the Katz-Master equation. And when t equals to 0, the initial conditions are chaotic to some g0 of v, which means the marginals, let's say fixed k marginals of L0n behave like g0 of v1 multiplied all the way to g0 of vk. then Kac showed that for future time, Fnt is also chaotic, let's say to some function gt of v. Moreover, what was interesting in Kac's case is that the limiting distribution gt to which the evolutions Fn of t are chaotic to satisfies an interesting PDE, which has the taste of Boltzmann's nonlinearity. Should we say anything here? This equation is known as the Katz-Boltzmann equation. We don't need to know the details at the moment. And the initial condition is, of course, G0 of V, where the initial conditions of Ftn were chaotic too. Okay, let's put a diagram. Let's do this. So this is Katz's result in a diagram. So if we start with the initial conditions Fn of 0 for various n, and if we let n go to 0, the marginals are chaotic to G0, we could go to the time evolution along the Katz master equation, which is a linear equation. This family in n, it's also going to be chaotic to G of t. Moreover, there is the evolution from G0 to G of t can be via the Boltzmann-Katz equation. So we can solve the lower line without going to the above, in the sense that this diagram is commutative. So this was Mark Katz's result. And some nice facts about this model is that for Katz's model, it turns out that the uniform distribution, where all the possible energy distributions, some of the VI squares are equally likely, is a stationary state, and that Katz's model is ergodic towards sigma n. And that's good news, because here, if we put an arrow and continue as time goes to infinity, this will take Fn of t to the uniform distribution sigma n. And it turns out that if we solve the Boltzmann-Katz equation, it's also ergodic to the Gaussian. And we have already seen that the uniform distribution is already chaotic to the Gaussian. So that's nice. The Boltzmann-Katz equation, which is nonlinear, is sometimes called the kinetic equation or the effective equation. And this process, which takes chaotic at time equals to 0 to chaoticity at future time, it's called propagation of chaos. And it's also used for other equations like Makin-Vlasov. But we will not deal with propagation of chaos. We will just deal with initial conditions chaoticity later on. Okay. So to introduce entropic chaoticity to motivate it, we know that if we have a convergence in the n-particle model, a nice measure is the relative entropy. The relative entropy is defined in terms of the relative density as r log r sigma n. I use a positive sign convention. And this is a good measure for two reasons. First, if the relative entropy goes to 0, then we know that the total variation of f and t with the limiting uniform distribution goes to 0 due to this inequality with many names, César-Kullbach inequality. And also, what's useful about relative entropy as opposed to the L2 metric, which Mark Kac used, is that this is extensive in n, which means morally that this object behaves like it's almost linear in n. So as the number of particles goes to infinity, this grows only linearly in n as opposed to geometrically in the L2 case. I said morally because if it were in Rn, not a sphere, that's the case. Okay, so the interesting thing is that if one can show for the time evolution model, if the relative entropy at time t decays at rate b of t independent of n, and this b of t goes to 0, so if there's a rate independent of n, and if we can say that the relative entropy of Fnt is approximately n times the relative entropy of a one-dimensional distribution, here gamma is the Gaussian with the same energy E. Then, going back to the propagation of chaos diagram, we can say that, okay, in future time, this is approaching the relative entropy of some function g of t, knowing relative to the equilibrium distribution gamma, and these are the initial conditions. We would inherit the convergence in relative entropy with the same rate beta. So if there's any evolution for which rate beta is known, that's good news if we could approximate the relative entropies also. I will specify this further. For the CATS model, Michel Amoureau did find a beta of t, and they found it's a power law. So that's good news. So we have convergence in relative entropy for the CATS model. But now we need to be more rigorous and specify how can we approximate the relative entropy of the n particle distribution by n times something which is related to one particle distribution. And here entropic chaoticity plays a very good role. So this is the definition of entropic chaoticity, which serves exactly for this purpose. So if for each n, we let Fn be a symmetric distribution on the sphere of radius Ne, and G a fixed measure on which has a finite relative entropy relative to the Gaussian, we say that Fn, the family Fn, is entropically chaotic to G if Fn is chaotic to G in the regular sense, meaning its marginals approach to products of G. And in addition, asymptotically for large n, the relative entropy of the Fn, it's n times the relative entropy of, this should be G relative to the Gaussian. So if we can say that for large n, Fn, even in relative entropy, it's like behaving like a power, then we say that the family Fn is not just chaotic, but entropically chaotic to our distribution G. Apologize for the typo. Okay, let's also define another kind of chaoticity, which will be useful for us. So, the G in the previous slide turned into F on this slide. So if we take any probability distribution F, its Fisher information relative to gamma is this object. So F has to be the relative density, which is rho, has to be very smooth and is integrable. And for distributions on spheres, we can simply similarly define the Fisher information relative to the uniform distribution sigma n on the sphere, and it's given by the square of the gradient, this integral. And here on the sphere, we use the spherical gradient. One thing I want to comment on the Fisher information is, of course, if F is not relatively continuous with respect to gamma or sigma n, then this is said to be infinite. And the relative Fisher information is also an extensive quantity in the sense that it also behaves like n times an object which is of order 1, morally. That's why in many of the measures, when we have convergence, we will have 1 over n times the relative Fisher information. Okay. Now that the Fisher information is defined, so we have chaoticity in the sense of Fisher information. So now let's consider a family of distributions on spheres of constant average energies, and let G be any probability density because it's absolutely continuous with respect to the Gaussian. G having finite Fisher information. Then we say that Fn is chaotic to G in the sense of Fisher information if, well, Fn is chaotic to G in the regular sense, in the sense of Mark Kac. And in addition, 1 over n times the relative Fisher information of Fn with respect to the uniform measure converges to the Fisher information of the function G, the limit G, with respect to the Gaussian. Okay. Are there any questions so far? Okay. Okay. Well, there's a relation between these different kinds of chaoticity. So there is a hierarchy. So I'm going to cite Michelet with a typo. Okay, Michelet and Horet, 2014. So if we take a sequence of a family Fn of symmetric functions whose, let's say, 6 moments are uniformly bounded in n, and let's assume that the first marginals are converge against continuous bounded functions to some g for some measure g. Remember, this is not chaoticity because it's only related to the 1 marginals. Then we have a hierarchy in the list. Each one implies a second one. The strongest is the Fisher-information chaoticity. So if the family Fn is Fisher-information chaotic, then to G, then it is Kac's chaotic to G, and I should have a 1 over n here. The 1 over n times the relative Fisher-information Fn sigma n is bounded for all n. This is not true if the factor 1 over n is not present. And if the second condition holds, then we are guaranteed to have entropic chaoticity. And if we have entropic chaoticity, by definition, we have the regular G chaoticity of the family Fn. So a result which is hiding behind this is the HWI inequality, where the relative entropy can be controlled by Wasserstein distance if the Fisher-information is controlled bounded. Okay, so now we want to introduce a family. So an interesting question is, if somebody gives you a probability measure, mu, and says, can you find me a family of measures Fn constrained to spheres such that this family is chaotic to mu? And you can ask if it is entropically chaotic to mu also. So this question was answered in 2009 by Carlin, Carvalho, Leroux, Michael Loss, and Villani with 4th moment, and then with 4th moment condition on the limiting measure f, and later improved to anything bigger than 2 moments by Hagop Tossounian and Ina. They said that if f is in L1 and LP for some p bigger than 1, and f has more than 2 moments, then what they do is they take the product, which would have been enough if we didn't have the energy constraint that the sum of the energies is n times E, and they normalize it on the sphere by the n of f. So this is the integral of f of b1, f of bn over the sphere. And they said this is a good candidate. Of course, this is well defined if f is continuous. Otherwise, the Zn of f is being integrated against on a set of measure 0. So changing f on a set of measure 0 can produce problems. So whether this is well defined or not. The good news is that when delta is bigger than 2 and p is bigger than 1, when n is large enough, I think it's p over p minus 1, then the n of f is uniquely defined. The conditioned states exist, these are well defined, and in addition, they are entropically chaotic to the distribution f that we started with. So we ask from f to be a density in L1, also in LP, and have enough moments. The proof is they try to show that there are nice central limit theorems, and they try to show that the n of f is at approximately 1 when n is large. But we want to introduce another family which does not have these constraints of not being well defined for small n. So now let's introduce the following family. we will take any probability measure f. For simplicity, let's say it doesn't have an atom at the origin, even though this can be treated. We define the rescale states fn hat on this constant energy spheres as follows. We take a vector of n IID f distributed vectors, and then if the length of the vector x1 to xn is not 0, then we rescale the vector square root of ne over the norm if the denominator is not 0. But if it happens to be 0, we just set it to be equal to one point on the sphere, one fixed point on the sphere otherwise. And let f hat n be the law of this random variable yn. So far we didn't need f hat n to be a density, and this is well defined. Okay, let's introduce the results. Okay, so this is work in preparation. So we require that f has a finite second moment e fixed, and we have the following results. If we put no more conditions on f, then the family f hat n is chaotic to f as n goes to infinity, and the metric that we use is 1 over n, the Wasserstein metric with f hat n with the full product, which is nice. But if we only have 2 moments, then we don't have any rates. We just know that it goes to 0, because behind this is a central limit theorem. If f is a probability measure and we ask for a moment, a more than fourth moment to be finite, then we still have chaoticity to the measure f. We still use a Wasserstein metric, which implies weak convergence. But in this case, as soon as we have more than 4 moments, we have a rate. There's a constant and over the square root of n. This star means that we can say more about it. If we just have 4 moments, then it's 1 over square root of n log n. And if we have any moment bigger than 2, there's a corresponding exponent, slightly worse. So this is just a weak form of chaos. We can say something in terms of the L1 metric, where we can compare the k-marginals. This is the projection onto Rk of the distribution f hat n. If we assume more than the second moment, and if we assume that f is almost Lipschitz, it belongs to this space L0R, which means that given any epsilon, f can be approximated in L1 by a Lipschitz function g epsilon, but the price of this approximation is that the Lipschitz constant of g might grow. Let's say it's L0 epsilon to the minus r geometrically. So if f belongs to this class of functions, so it's a then we can have an explicit rate in L1, and the constant gets worse as delta goes to 0, or if r goes to infinity. It is explicit. We can mention it later. Next, so if we again assume that our energy is E, and if we assume that we are on a density and the relative entropy of f with respect to the Gaussian is finite, then we can say, aha, we have convergence in relative entropy. This object goes to 0. This was f hat n, the entropy of f hat n is close to n times the entropy of f without rates. But if we assume that f is a density, if its relative Fisher-information of f, the limiting measure, is with respect to the Gaussian is finite, and if we have enough moments, then we have again convergence in chaoticity in the sense of relative entropy. We also have rates, and we can choose eta, any number, basically this exponent minus epsilon. Here k is the moment, and k is not the number of variables, it's the moment. Finally, if f is a density in R and its relative Fisher-information with respect to the Gaussian is finite, then we also have Fisher-information chaos, and that's good news because. But at the moment, we don't have rates. And I want to mention a few things about the ideas of the in the proof that we used. So we relied on many results which were already known. So two of the main ideas of the proof are this asymptotic upper semi-extensivity. Morally, if you have fixed a base space, let's say the dimension, let's say it's RD, R to the n0, and if you have a sequence of measures, let's say densities, Fn on the same base space which converge weakly to a limit f infinity, and if you take any convex functional, then j of the lim inf of jf will usually be bigger than j of the limit. So what happens is that this is true if in our cases for the relative entropy functional and the Fisher-information functional, even though the spaces n are changing. For example, this one I'm citing Carvalho, Losleroy and Villain's paper. So if the I forgot to mention that these are symmetric distributions, and if let's say the one particle margin converges weakly to f, then we have this inequality. So this was good. And also, I think, if I'm not mistaken, Horin and Michelet have it for the Fisher-information, a similar inequality. So for our rescale states, we only have to worry about the other side of the inequality. And a nice example, a nice handy tool that we had is that the f hat n, the rescale states, can be written in a nice form. In the integral, I think the zero should be excluded from the integral. They can be represented as a convex integral where the integral of w of r dr is just 1, and here the well, by convexity, Jensen's inequality serves as a very useful tool for us. So before going, I think these are the main parts which I wanted to present. There are a couple of slides in the appendix, and I want to thank all of you. I apologize for not being able to put a nice thank you figure. I didn't want to pay stock exchange photos in the last moment. Are there any questions so far? Well, I can ask my collaborator Roberto if I said something wrong, he can let me know. So that is my question. In the meantime, okay, let me use this opportunity to say something about this space of Lipschitz functions. It's that the functions are not Lipschitz, but they can be approximated by Lipschitz functions. A class of examples I had in mind is functions which blow up, but with a power singularity. For example, x to the a when a is negative. Here L0 would be some constant. And the cost in epsilon to the r, it's related to a. So if a is 0, then we have here. And we can have jump discontinuities. So these functions would also be in these kinds of Lipschitz spaces. So a classical example I have in mind is you take a Lipschitz function and you perturb it by jumps and blowups of controlled a. A cannot be too close to -1. then these would be in the Lipschitz functions, which I mentioned. And we can also have any Hölder continuous function with the control tail. In this case, they are also approximately Lipschitz.
So thank you a lot, Hagop. So I propose that we unmute ourselves and thanks, Hagop. And so I open the mics for questions. So are there any? So Hagop already.
Okay. Maybe I can.
Sorry.
Hagop?
Yes.
Yeah, perhaps you can try to explain a little further what are the main differences between the rescaling and between the conditioned tensor product.
Okay.
Just in general, just to give an idea of what is the main novelty of this rescaling procedure.
Oh, thank you. So one thing is that the conditioned states demands a lot from F, that it be in LP and have enough moments. And it's well defined when N is large enough. In our case, we can allow measures, atoms. And it's well defined and it is chaotic without requiring F to be density, just second moment. And another thing, morally, when we're trying to simulate, I think conditioning, it means you take, you sample x1 to xn and you accept it if its energy, sum of the xi squared, exactly happens to be equal to N.E. So which means you're accepting a set of measure 0. But the rescale states, which are much simpler, and we just reject just in case the vector happens to be 0. So we reject only on a set of measure 0. So that's useful. So that's.
So I had a question, but I exactly needed this slide. Like I couldn't recall exactly. What is the magic of the sixth moment? So this is the first time I see a sixth moment being. Is this expected to be tight?
Yes, this sixth moment is here, and also it is in. Can I go 2 slides up? Also in no, in here. So Michler and Horet also use the sixth moment. So because we use Michler and Horet's result that 2 implies 3 with the rate, because we could show that our entropies stay uniformly bounded with the 1 over n, and we inherited his result. So I forgot how Michler and Horet used this. But tail controls are usually useful.
Yes, so, but is it expected this is a tight condition? So if you don't have sixth moment, this doesn't work, or should it work also with let's say second moment?
They give rates. Let me go down again. No, they guarantee that their rates work only if k is bigger than the sixth moment. I do not see a problem with the exponent if k is anything bigger than 2, but the proof is missing. So that's a good question if this can be extended for letter k.
I see. Thank you.
Thank you.
So are there any other questions? Let's see. So if not, I propose that we thank the speaker again. Thank you. And we can start the informal part of the